show the other method called contraposition. And it's very similar, and it's based on the inference rule that we saw in chapter 1, basically. And that rule says the following. If you prove that the not Q implies the not P, then you can consider that you proved what? P implies Q. So that's, because if you prove, because this is your original statement, you do the contraposition. That's not negation. That's a statement that's equivalent to yours. And this is obviously logically correct. Do we all understand that when you prove things by contraposition, that should be valid? So once again, the way here you don't reach contradiction at the end. What you are doing, you are trading your statement. You don't like your statement, you are trading it for a different one, and then if you prove the different one, this inference rule just justifies your procedure and accepts that as a proof of original state. There is no contradiction here. And yes?
Is that what we could have done to the previous example?
Probably not, because it's not implication.
Okay.
So usually works when there is implication. So here's one example. Original statement that we need to prove is if n squared is odd, then n is also odd. So do you see implies here, yes or no? If then. And it has a structure, P implies Q. So if this is P, and if this is Q, then you really have the structure P implies Q. But why is it that I don't like this implication the way it is? Why would I rather, yes?
Because P is n squared is odd, it makes more sense if we test by cases. If the Q comes first, then we can check if n is even or n is odd, and then we can square that.
So the reason is, look, here I'm starting assuming something on complicated object, and I need to derive something for a simple object. If you go from complicated to simple, you need to do heavy algebra. When you go from a square to n, what do you need to do basically? Square rooting, do you agree? Yeah. Square rooting is a tough operation. But if I go from right to left, I go from simple to complicated. That's always better. So that's why instead of concluding from n squared toward n, you will see my algebra at a certain moment. At a certain moment, either I need to square root or I need to square. What would I rather? I would square rather because that's much easier. So we say the following. Instead of this, we prove that the not Q implies not P. Is that basically equally valid thing, yes or no? That's what this rule allows you to prove by contraposition. So that means what do I want to prove? So I need to prove. No one gives me that. I still have to do the work to prove the following. What? If n, what?
Is either even or odd.
No. What's negation of n is odd?
N is even.
Not.
No. N is not odd. And then,
N is even, right?
if n is not odd, then what?
N squared is not odd.
Exactly. So I did just negations and flip them. Is this the way to do it? Don't rush it here. Maybe you can make some shortcuts. I don't want you to do them here. Then n squared is not odd. If you want, I can actually write it with O predicate, so it looks even simpler. I want to say not O of n implies not O of n squared. Do you agree? There is something that's better than something that's worse. What's better? I do derivation from simple to more complicated. Do you agree? From n toward n squared. What's bad?
I have a question. Why can't we just say if n is even, then n squared is even? Isn't that the same?
you did tons of logical conclusions and called tons of theorems, so you skip like 12 lines, which is correct, but I want to see those lines. So here's what I just did. So once again, that's how machines do things. So a machine says, all right, do contraposition with zero knowledge. So what did I do? I just flip them and attach negation. Why is this also good? There's no risk that I messed up something, do you agree? So that's it. So I didn't do any other conclusions. I just flipped them and attached negation. So now I start. Let n be an arbitrary integer such that n is not odd. What can we conclude now? From the theorem that we just discussed a minute ago, I know that for every number m, even of m or odd of m. Did we prove that a minute ago, that every number is either even or odd? So is it true for my number n that I started to discuss? So if it's true for everybody, it must be true for my number n. So my number n is either even or odd. But what else? Do I know that my number is not odd, yes or no? So if my number is not odd, then it must be one of those. What's the only remaining case?
For the every n element, should you include n's nots both, or
What's A?
the,
That's also true, but I don't need it. I just write what I need. Yes, it's one of them, but not both. But I call that for every m, this is true. That's what we proved a minute ago. If it's true for everybody, and it will be true forever, so I don't need to prove it all the time, then it's true for that little number, let n be, if you are kind of here a little bit confused that n is fixed and n is for every, maybe you can put a little n0 here to emphasize psychologically that your n0 is kind of fixed number undisclosed. And then what? I know that E of n0 or odd of n0, but I also know that it's not O of n0. So what can you conclude from these two?
therefore e of n0?
It's E of n0. And I'll do the argument here. Why? Because you have, if you have P or Q and a not P, you can conclude Q. Do you agree? That's an inference rule from propositional calculus that we know from before. So one way or the other, I know that E of n0. So what then? If E of n0, what does it mean if n0 is even? That n0 is what? Equal to what?
2k.
n0 equals 2k. So what happened so far? Look what I did. Is the whole story about the little n0, yes or no? But what was my progress from this line to that line? I had some ambiguous statement. I'm not being odd. That's very non-operational. Why? Because it doesn't say it is not. And being odd, I don't know how to operate that. So I was using the logic and definition. Here is where we are winning. We win when we have equation. n0 equals 2k. Now algebra kicks in. So now my information about n0 is the best possible one. Equation. Now I go to think about n squared, because at the end I need to prove something about n squared, do you agree? So what do I know now? n0 squared is what?
2k squared.
Which is what? 4k squared, do you agree? Well, now I know algebra, and that's definitely what we don't deny, which is what? 2 times 2k squared. What is that telling you about n0 squared? Why? Do I have a witness for n0 squared being even, yes or no? So I conclude that n0 squared is even. And now I will call, if it's even, it cannot be what? Odd. So I'll say the following. If P, and not true that P and Q, what can I conclude? If one of them and not both, who has to fail? Q. And that's exactly what I use. So if n0 squared is even, and then n0 squared cannot be both, like everybody else, even and odd, n0 squared is what? Being even, it is not odd. And that's what we need. What we did is we assume that n0 is not odd, and we concluded that n0 squared is not odd. Now we call contraposition, and then our original statement is true. So you need to understand, so when do you use contraposition? When you would rather reverse the flow of argument to go from right to left, but of course you have to do contraposition correctly, to negate the right side, negate the left side, flip them, and now you go from right to left in a way, but of course with negative statements, and that's needs little work. So you see, I paid the price. Original statements were nicer, with negation they are worse, but flow was more natural, from simple to more complicated. And that's why my algebra here was very simple. If I went the other way around, I would do square root, and I would have no ways to make any conclusions. So that's why this shows you what's important. Do you have a question?
What's the character in the parentheses, the second O at the bottom?
Oh, this one?
Yeah.
N, it's N.
Okay.
With 0 is always N. You don't need that 0, it's just psychologically, as I said, to contrast this M is running for every M. And of course, especially for simple statement, we don't do all that writing. Actually, what you said, we immediately skip all those tons of steps. But I want you to show me on these simple statements that actually you can carry the methodology. So what did we see? One example of this and one example of this. So on contradiction, as I said, you want this, what's below, and then you trade it for something else. When you succeed, you call this argument to justify. The same thing here. I want P implies Q, but instead, for some reason, I would rather prove this. However you prove it, when you are done, you call this to justify. Yes?
Can you explain the P not Q and P therefore not Q?
On this one? Basically, this is a valid argument. You can make a table easily to see that that's true, but it's common sense logic, I would say. Why? Because if it says that P is true, and it cannot be both, then one of them has to fail.
Yeah.
And P cannot fail, obviously, so who has to fail? Q. So that's the reasoning that I use there. As I said, we very often skip those. You never thought about it, why something looks good to you. You don't call the precise argument, but that's why here we make this almost mechanical process, where you call the appropriate inference rule or appropriate tautology to justify why is your passage correct, or to avoid passage that's not correct. For example, you know how many times through the history of mathematics people say, it's easy to see. And then later on, we kill ourselves trying to see it, or later on we show it's not true at all. So that's very dangerous when there are some things that are skipped, like there are no, they're just tedious to write down. And we always say in mathematics, and that's where rigor of mathematics works. Whenever we skip something, we can write down every little detail if challenged. And of course, who's going to write all this when things get really complicated? You have calculus 3 theorem, and you want to write all this, it takes forever. But there are some things that people try to develop through history, like automatic provers and all that. So that's another story about this. All right. We saw both methods. Now we want to see illustration of those two methods in two very important mathematical statements historically. And here is what they are. So first statement is that square root of 2 is irrational number. Is irrational. This was historically very important result in mathematics. Because, for example, I don't know how it was reflected in other world mathematics, but I know in Greek mathematics, you have like 6th century BC, and before that period, people always thought that the only numbers that exist are fractions. Why? So, mathematics was not like someone teaches you what was developed for centuries. People need something and they invent little tricks, and then that's what how mathematics grows. So they say, do you understand why would people talk about these objects? Yes or no? Because you see 1, 2, 3 apples, 4 apples, and you start kind of to talk about it in an abstract way. Surprisingly enough, Greeks didn't know about negative numbers. Negative numbers didn't appear in mathematics until 15th century. I cannot believe it. It looks so natural. It's like nobody did mathematics in Minnesota or something, when it's really, when it gets cold, So anyway, they didn't know about negative numbers, but they did know about fractions. Why? Because you had like 2 acres of land, and you had 3 sons, and you wanted to divide those 2 acres equally. That's 2/3. So that all these problems were generally developed around land, how to divide land and all that. So people were working with the fractions like this. So I had 2 pieces of something and divided, or they took 1 piece, divided into equally, and then repeated that twice, or something like that. So they develop a feeling for fractions. Okay. And then comes that period when square root of 2 showed up. First, how did it show up? Why do you need it when you don't divide land? Because of the famous theorem that says the following. I have a land, and then here is 1, here is 1, and then I want to walk here. And how much is that? The Pythagorean theorem, that's 6th century BC, square root of 2. Agreed? Some number, however they called it, whatever they described, that's square root of 2. And then they said, all right, but that should be one of these numbers. There are no other numbers but fractions. So it should be a fraction. And to their surprise, it's not a fraction. So for them, it is not what it has to be. And that's big thing. That's just, the whole civilization, it's not like one person got confused. The whole civilization had no idea that they will need some deeper analysis for numbers. And that's what happens here, actually. How do you prove that square root of 2 cannot be written as a fraction? Why not? It might be someone writes, and then, so can square root of 2 be 142 over 101, for example?
Sort of.
Yeah, they didn't have calculators, so generally, if you take this number 142, 101, and square it, you will really get something that's very close to 2. Right? You can say, oh, right, if I tried harder, if it's 7, 10, 15 decimals, I would do better. But generally, that can never happen. And here is the proof that we want to see. It was a very important historically, as I said. So proof. We'll argue by contradiction. So that means we'll assume what? Negation of P, what would that be?
2 is rational.
That square root of 2 is rational. That's all. So square root of 2 is rational. What does it mean that number is rational? That word is just to be fraction. Is that fraction of 2 integers? So now I assume this is my not P. So my goal is now to reach what? From not
C.
P, I want to reach contradiction, and then I'll say, you see how wrong it was? You have to assume it. So here it is, not P is that square root of 2 is rational. Why would that lead to contradiction? So here it is. So So square root of 2 being irrational means it's equal, is that what we said? Being rational is m over n, do you agree? And what else? N cannot be what? Zero. But there is something else, and that is, can I assume that m and n are relatively prime? That means that they don't have common factors. That the fraction is reduced. You remember what does it mean that fraction is reduced? If they have a common factor, can I cancel it, yes or no? And then what? Until that finally there are no more factors. This cannot go forever because finite numbers cannot have infinitely many factors. So generally I can assume, and this is crucial, and in math we say that WLOG, and that stays without loss of generality. I'm not assuming anything special. This has to be true. That's why I'm assuming it. That's why we say vlog. So vlog, I assume, that's not special assumption, that the fraction is reduced which means that m and n are relatively prime. Relatively prime. And that's a crucial assumption. All right. So if this is the case, that means what? What is square root of 2, basically? What do we call square root of 2? That's a number. When you square it, what do you get? 2. 2. So I square both sides. Square. Both sides. What do I get? 2 equals over By the way, this problem I very often assign on the exams, either on rel or on the final. And I don't think that I ever got more than 30% response. And I don't know why. This is not rocket science. And you tell me, there is some passage that's like, wow, who would have thought of this? So, this is fairly simple idea, but just you need to carry it carefully. And then whenever some detail is not clear, feel free to ask me, why is this line following? So here it is. Can I multiply both sides by n squared, yes or no? Yes. So what do I get then? Algebra. 2n squares equals n squared. Yes.
Why are we allowed to square root now?
No, we are not square rooting, we are squaring.
I mean, oh, okay.
We are squaring. Why? Because that's what square root of 2 means.
Okay.
Square root of 2, what is square root of 2? That's a number that when you multiply it by itself, you get 2. There's no other description of square root of 2. So then when I square, and that's a property of equation, you can always square left and right side.
Okay.
And here's the crucial spot. What can you tell me about left side? Can you tell me if it's even or odd, or you cannot conclude? Are you sure that left side is even?
Yes.
Why? Because there is that's witness 2 times something, do you agree?
Yeah.
Then what can I conclude about right side? Is the right side also even? So m squared, so I conclude m squared is even, and you can say as a witness. Who is the witness? N squared is your q. 2 times the witness is n squared. Or you don't have to say it that way. You can say because n equals 2 times whatever. Do you agree? Or just say by definition. So that language, could go different ways. Now, did we prove a minute ago? If a square is even, does number need to be even? Did we prove that a minute ago on contraposition? So according to previous theorem, and you can call theorem that we proved in class, m also must be even. So this is a valid theorem, and that's how math knowledge works. You have a theorem and you call it. The only problem is that you cannot read it, so I write it again. According to preceding theorem, contradiction. Since m squared is even, m is also even. Everybody agrees with this? Yes.
How do we know m squared is even?
That's because here it is. It is 2 times something. That's by definition.
I understand that that one's even, but then how do we have m?
If you are equal, all your properties are the same.
That's already a theorem, right? And
No. He's asking about something else. That's property of equal. If something's equal to my glasses case, it must be glass. It must contain glasses, be brown, round. Everything you
But
assume.
see, it's 2 times something equals something.
Yes. So here it is.
Something different.
So it makes it even.
So wait a minute. When are you allowed to say that someone is even? If you can write it as 2 times q. Do you see your q?
Yeah, I'm good with that.
That's it.
But then, okay.
So definition says, even of S is equivalent that there exists Q such that S equals 2Q. So this, check this and you are okay. Do I have my Q? Who is it?
N squared.
That's it.
Okay.
That's how you test
So m
something.
squared has to be.
Yeah.
Okay.
So that's your witness. That's why I say witness is N squared. Anyway, it's very good that you ask those questions because we are splitting the hair. That means we should split it then, because otherwise, if we skip, some details and kind of, fully cover the others, that doesn't make sense. So it's very good. All right. So now I know that who is even? M is even. If M is even, what does it mean by definition? That M equals what? 2 times some K. Is K used anywhere else? In my proof? No. So no options. And here comes the best part. Let me feed it now in this equation. So the equation now says what? 2n squared equals what? 2k and n squared. Agreed? And that's what it is. Since your square has 2, you get 2, but when you get 2, you actually get 4. Now you get even more than you were entitled for, and that's what makes this such a nice argument. Let's look at this now. Let me square the right side. Now algebra, my favorite, is squared. 4k squared. Can I divide by 2 both sides? So what do I get? N squared equals what?
2k squared.
Now the sides are changed. Who has 2? Who is now even?
N.
N squared is even. Why? Here's your witness. So n squared is even. But because of the same theorem, what happens?
We run around in circles.
No, I'm not running in circles. I'm actually reaching contradiction. Because now, if n squared is even, for the same reason as here, when your square is even, do you need to be even? Yes or no? So who needs to be even? N. So n is also even. Which is for the same reason as this, if this is 2 stars. 2 stars again, so that I don't copy the argument. So what's wrong? Nice. N is even, yes.
Well, if m and n are even, then they're not relatively prime.
That's your contradiction. Here is your contradiction with the assumption. I assume that I clean them and that they cannot share the same factor. But what happened? N is even and m is even. Do they have a common factor? 2. So m and n are not relatively prime, and I assume that they are. Here's your contradiction. And let me finish and I'll answer the questions. So altogether, what happened in the structure? So once again, assuming the square root of 2 is rational, that it's a fraction, I derive the contradiction. So my not p gave me contradiction, so my p must be true. So square root of 2 is what? Irrational. So that's why it is valid. So now I have the question of comment. What I can, yeah.
So if this result is test, we also have to prove that if m squared is even, n is also even.
I have to give you the instruction about this. So usually if I ask you this on the test, I would let you call it. But if you have dilemmas, what is it that you can call, just ask. Okay? Now what? Now if you look at many exams that I assign in this course, you can see that I vary this idea very often. So for example, how would you prove that square root of 3 is irrational? For square root of 3, it's not going to be even or odd. And I see people sometimes, I assign on the exam square root of 3, and they start talking even or odd. Why would the divisibility by 3 care about even or odd? What does divisibility by 3 cares about? Remainder dividing by 3. So you have how many cases? 3 cases. So 3k plus 1 and 3k plus 2, do you agree? Generally what you need there, just let me make that comment and I answer a question. You need that to prove the theorem. If a square is divisible by 3, then what number itself is divisible by 3? How would you prove that one? The same way as I did with 2, with contraposition, but you don't have only 2 cases. How many cases do we have? N is 3k plus 1, or what? 3k plus 2. So think of that adjustment of the proof for modulo 3 or modulo 5, just 5 cases or something like that. And then I also ask the following question. Well, for example, how about square root of 3 plus square root of 2? Would that be even or odd? Oh, no, I'm sorry. Square root of 3 plus square root of 2. Is that rational or irrational?
Irrational.
How do you know? 2 irrationals can give you rational when you add them up. Be careful. So you cannot call that argument. Because what? Because here it is. Is square root of 2 rational or irrational?
Irrational.
What about negative square root of 2? Rational or irrational? Add them up. Rational or irrational? So don't think about it that way. But why would square root of 2 plus square root of 3? And as I said, now you will see that in the homework. Think about it. You need to adjust. For example, assume that square root of 2 plus square root of 3 is rational. Okay? Now, if it's rational, when I square it, would that also be rational? Yes or no? Yeah. Or, no, it's even better. No. If this is rational, would the reciprocal also be rational? Yes or no? But, so reciprocal would be, that would not help. Sorry. No. No, square it. That would work. Square root of 2 plus square root of 3 when you square it. Would that be rational as well? Yes or no? And how much is that? That's 5 plus 2 root 6. If this was rational, who would be rational as well? And then root 6 you prove the same way, 6 cases. So generally there is little work around it, little problem solving, and I'll answer questions about that type next time. I want you to see the main theorem. I want everybody in class to know the main theorem at least. As I say, I very often assign exactly the main theorem, and I'm not happy how my classes respond. And let's clear it. Either not too much time today, but on Wednesday and so on. Yes.
So instead of doing 6 cases there, could you prove that they're rational separately? Could you prove that root 2 is rational and root 3 is rational, and therefore add 2 rational
Product of irrationals could be rational. So it's not going to help. You have to be careful. What are the statements that you are calling? Are they true or not? And in general, very often they are not. All right. Let me show you one more of those famous theorems so that we have them in class. As I said, there's lots of problem solving. There's lots of things now technically to learn about it. First, you want to learn the basic statement and its philosophy, and then we'll talk more about variations answering your question. The second one is the following. How many prime numbers are there?
Infinite.
So, statement says there are infinitely many primes. Example 2. There are infinitely many By the way, how many? Well, I mean, how frequent are they? So there are infinitely many, but Do they go to infinity the order of magnitude of n or square root of n or something like that? That's an interesting question, and people resolved that 150 years ago. So, we will comment that. But this is very easy. This is like, 2,000 years ago. So, why there are infinitely many primes? Because you might be afraid, you get new and new primes, and suddenly it might be that whoever you try, there are so many candidates, you are forced to be divisible by someone below you. Is that reasonable to assume? And here is a very quick and elegant proof that cannot happen, that there are always enough primes that always new numbers come. Yes?
Would using something like a series and showing that it diverges or something, is that?
Series, that would be like a limit or something.
Yeah,
So,
taking the limit of a series and showing that
so
diverges.
that would be maybe an argument, if you can find something equivalent. That would be an interesting thing. Why? Because if you would make something that's function of primes, and then you do the sum, and all the finite sums converge, do you agree? So if you show that it diverges, then you are showing that there are infinitely many numbers. That would be a nice, interesting proof. And I think there are some arguments of that type that I saw somewhere. Yes?
Would the problem with that being it's hard to define how you would say what all the primes are in a limit, right? Is that what the difficulty in that is?
No, yes, but on that one you have to control that sum and to skillfully make that function. And there's much easier way. What you'll see here is very, very basic actually, when you're surprised how it works. So what? We'll use contradiction again. So we want the following. We want to get P, but instead of that, what are we going to prove? Implies contradiction. So I will assume not P. So what's not P? There are how many? Not infinitely, but what?
Limited.
Finitely many. Finitely many. So what? If there are finitely many, I can list them all. Do you agree? So here is the list. List of them. P1, P2, P3, and the last one will be, let's say, PK. And that's it. I have all the primes. It's a long, long list, but at the end there's last prime, no more primes after that. So what can we do then? I will make the following number. I'll make a number A, and that number will look like this. I will multiply them all times P3 times Pk, and I will add 1. Okay? Huge number, hard to imagine. Doesn't matter. In theoretical mathematics, we don't care about it. We make objects that we like. All right. So what can I tell you about A? Did we have a theorem saying that every integer bigger than 1, and this was obviously bigger than 1, has a prime factor? Did we say that? So does A also need to have a prime factor? Yes or no? Everybody has it, so A has it. So since every number, since every integer greater than 1 has a prime factor, A also has a prime factor. Okay? So what then? If A has a prime factor, who is it? Is that factor somewhere in the list, yes or no? Yes or no? What? There are no others. Here are all the primes. So if you tell me ever prime, it must be there, because that's what I thought. That here we listed all the prime numbers. So the moment when you say, oh, I have my prime, is it on the list? There's nobody outside of the list. Everybody's here. So your prime factor must be one of those, do you agree? So there might be more than one. So one of them, let one of them be Pi. Pi is one of those, wherever it is. ith in the order. So what then? So my number A is divisible by pi, which means, so A equals what? Pi times what? Times K. I cannot use K. Q. Is it nicely divisible? Is that what we assume? So how much is the remainder when you are nicely divisible? But let me look here. Is pi somewhere here, yes or no? So this looks like, let me call all the others q prime. So it looks like pi times q prime plus 1. So what's your remainder modulo pi? What's your remainder here? What's your remainder here? How many remainders do you have? That's impossible. So you cannot have two remainders modulo pi, because you cannot at the same time be divisible by pi and give remainder 1. Here's your contradiction. Because the remainder of a modulo pi is 0, and the remainder a modulo pi is 1, quotient remainder says 0 equals 1. Here's your contradiction. So assumption that there are finitely many primes, broad contradiction.